Tonight, we sit with one of the strangest possibilities the universe has ever offered us. The idea that everything around you may have happened before and may happen again. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. So, let your shoulders drop. Let your breathing slow. We are about to drift outward, past the ceiling, past the clouds, past the moon, until the earth becomes a small blue marble behind us, and the sun is just one warm light among billions. Imagine pulling back farther still. The solar system shrinks to a dot. Our galaxy, the Milky Way, spirals into view, a slow pinwheel of pale gold and dusty rose. Pull back again, and the Milky Way becomes one bright speck in a vast web of galaxies, strung along glowing filaments, like dew on a spider's thread. This is the cosmos at its grandest scale. It looks finished, settled, eternal, but it is not settled. The whole thing is moving. Every cluster of galaxies is drifting away from every other cluster, the space between them quietly stretching like the slow rise of bread in a warm kitchen. Run that motion backward in your mind, and everything comes together. The galaxies fold inward. The light grows fierce. The cosmos shrinks to a point so small and so hot that our physics simply stops being able to describe it. We call that moment the Big Bang, and for a long time, most of us pictured it as the beginning, the first page, the opening note. Tonight's question is softer and stranger than that. What if it was not the first page at all? What if the Big Bang was simply the latest beat in a slow, patient rhythm? What if our universe is one breath in a chest that has been rising and falling for longer than any clock could measure? This is the idea of a cyclic cosmos, a universe that expands, slows, gathers itself back in, and then begins again. Or a universe that does not crunch at all, but somehow passes through a kind of doorway, where one age closes and another quietly opens. Some thinkers have imagined endless bounces, each one wiping the slate almost clean. Others have imagined endless aeons, each ending shaping the conditions of the next, like footprints left on a tide-smoothed beach. The honest truth is that we do not know. We do not know if the universe began once, or if it has been beginning gently, over and over, since before there was a word for time. We do not know if anything from a previous cycle could reach us here, in this one, and we do not know if we will ever find a way to tell what. We do have our theories, and they disagree with one another in beautiful ways. Some physicists picture two great sheets of higher dimensional space drifting toward each other and softly colliding, sparking what we call a Big Bang on each surface. Others picture the universe stretching so far and so thin that it forgets its own size, and that forgetting becomes the seed of a fresh young cosmos. Still others use a kind of quantum mathematics to suggest that the singularity at the heart of the bang was never really a singularity at all, but a bounce where a previous universe collapsed almost to a point and then sprang outward again. Each of these ideas is a candle in a very dark room. None of them yet has the kind of evidence that would settle the matter. The classical picture of a universe that crunches back together has lost ground in recent decades, because the expansion we see today seems to be speeding up rather than slowing down, and yet new versions of the cyclic idea keep appearing, each one trying to fit the strange facts we have measured. Across the next many hours, we will wander slowly through these possibilities. We will sit beside the cold echo of the early cosmos, the faint glow we call the cosmic microwave background, and ask whether anything unusual hides in its patterns. We will visit the quiet mathematics of bouncing branes, the dreamlike geometry of conformal cycles, and the puzzle of entropy, the stubborn way disorder seems to grow and never reverse. For tonight, though, this first section asks only that you hold the question loosely, the way you might hold a smooth stone in your palm. The universe may have been here before, here. It may be here again, and while you drift off, we will wonder, gently, what that might mean. Let's begin with the simplest version of the question, the one a child might ask while looking up at the night sky. What if the universe did not start? What if, instead, it has always been here, breathing in and out, expanding and contracting, again and again, with no first breath and no final one? To sit with that idea, we need a few gentle facts to hold in our hands. The universe, as we measure it today, is about 13.8 billion years old. That number comes from the faint light still drifting through space, light that began its long crossing when the cosmos was young and hot. We can read that light the way you might read the rings of a very old tree. Each ring tells a story of weather long past, and each pattern in that ancient light tells the story of a much younger cosmos. 13.8 billion years is a number too large to feel. So picture it this way: if the whole age of the universe was squeezed into a single calendar year, then all of recorded human history would fit into the last 14 seconds before midnight on December 31st. Everything you have ever read about, every empire, every song, every grandparent, every loaf of bread, all of it tucked into those final breaths of the cosmic year. The rest of the year belongs to stars, to galaxies, to slow swirling clouds of gas, and to silence. Now, the universe is also unimaginably large. The part we can see, called the observable universe, stretches about 93 billion light years across. Light year is the distance light travels in 1 year, and light is the fastest thing there is. Even moving that quickly, a beam would need 93 billion years to cross from one edge of our view to the other. Beyond that edge there is almost certainly more, perhaps endlessly more, but we cannot see it. Light from those farther places has not had time to reach us yet. Inside this enormous bubble float about 2 trillion galaxies, give or take. Each galaxy holds hundreds of billions of stars. Each star may hold planets, moons, dust, ice, and quiet little worlds we will never name. The numbers stop meaning much after a while. They become a kind of music, a low hum of zeros. Now hold all of that in mind and ask the question this episode is built around. Did all of this begin once, in a single hot flash, 13.8 billion years ago? Or did that flash come at the end of something else, and the something else at the end of something before that? On and on, with no first page in the book. This is the heart of the cyclic idea. In its plainest form, a cyclic cosmos is one that expands, slows, falls back together, and then somehow rebounds into a new expansion. Or it stretches so far and so thin that it forgets its own size and starts fresh. The details depend on which theory you ask. Some of these theories use colliding sheets of higher space. Some use a quantum nudge that prevents a true crushing point. Some use a strange mathematical trick where the cold, empty end of one universe looks geometrically like the hot, dense beginning of the next. We will sit with each of these in their own time. For now, only the picture matters. Imagine a tide. It rolls in, foams against the sand, and pulls back. It rolls in again. The water is the same water, more or less, but the shape of the wave is new each time. A cyclic universe is something like that tide. except the waves take many billions of years to crest, and we are tiny living things floating somewhere inside one of them. There is also a competing view, and it is just as old and just as serious. In that view, our universe began only once, from conditions we do not fully understand, and it will simply keep expanding forever, growing colder and lonelier, until even atoms come undone. No bounce, no return, one long arc with two open ends. Both pictures fit the evidence we have today. That is the strange and beautiful part. The faint light we measure, the distances we calculate, the rate at which galaxies drift apart. None of these, on their own, tell us whether our cosmos is a single shot or a single beat in a slow eternal drum. The mystery hides in the silence before the bang, in the whisper we cannot quite hear. And it is from that whisper that the rest of this long, slow night will unfold. Long before telescopes, long before equations, people looked up at the night sky and wondered if the world had a beginning. Some watched the stars wheel through the seasons and saw a kind of pattern. Spring followed winter. Day followed night. The moon waxed, waned, and returned. From these gentle rhythms, an idea began to form. Perhaps the cosmos itself moved in circles, returning to where it once was, again and again, with no true first day and no true last. This idea is very old. It shows up in the writings of thinkers in ancient India who imagined the universe breathing in and out over vast stretches of time. They spoke of long days and long nights for the cosmos, each one lasting billions of years. When the cosmos breathed in, everything gathered. When it breathed out, everything spread. The numbers in some of these old texts are startlingly large, far larger than anyone in that era had any reason to picture. Greek thinkers played with similar pictures. The Stoics, a school of philosophers in ancient Athens and Rome, spoke of a great fire that would one day consume the world. After the fire, they said, the world would form again exactly as before, down to the smallest detail. They called this idea eternal return. Every life would be lived again, every conversation repeated. It was a strange and somewhat haunting vision, but it grew from a simple instinct. If nature loves cycles, then maybe the largest thing of all moves in a cycle too. These were not scientific theories in the modern sense. There were no measurements, no equations, no tests. They were guesses born from watching the world and noticing how often things came back around. Still, the seed was planted. The idea that the universe might repeat in some form became one of the oldest hunches in human thought. For most of history, this hunch sat quietly beside another idea. Its opposite, many traditions held that the cosmos had a single beginning and would have a single end. One straight line from start to finish. Both pictures were possible. Both felt true to someone. Nobody could yet tell which, if either, matched reality. Science only began to seriously enter this conversation in the 20th century. Until then, most astronomers assumed the universe was simply static. It would always be here. The stars sat in their places, more or less, and the cosmos as a whole did nothing dramatic. This was the quiet background assumption of nearly every serious thinker for centuries. That assumption began to crack in the 1920s, when observations of distant galaxies suggested they were moving away from us. The universe, it seemed, was not still. It was growing. Running this growth backward led to a startling conclusion. If everything is rushing apart now, then long ago everything must have been close together, perhaps unimaginably close, perhaps gathered into a single dense point. This was the rough seed of what we now call the Big Bang. And almost as soon as the idea took shape, The old hunch about cycles came back. If the universe expanded from a tiny, dense state, could it one day stop expanding, fall back together, and bounce again? Could what we call the beginning simply be the latest bounce in a much older story? In the middle of the 20th century, this question was taken seriously by working scientists. The picture they sketched was called the oscillating universe. In it, the cosmos expands for billions of years, slows, halts, and then collapses. At the bottom of that collapse, something happens. Maybe a new bang, maybe a soft rebound, and then expansion begins again. A breathing cosmos in a new mathematical dress. For a time, this was a respected possibility. It had a certain elegance. It removed the awkward question of what came before the beginning. Because there was no single beginning, it echoed the old intuitions of ancient thinkers, only now wrapped in the language of general relativity, the modern theory of gravity that links space, time, matter, and motion into one framework. But problems began to surface. Some were technical, some were philosophical. Could a universe really survive its own collapse and emerge whole on the other side? Would each new cycle look like the one before, or would something slowly drift cycle by cycle until the rhythm broke down? These questions did not have easy answers. They still do not. The old idea of eternal return had returned, dressed in equations. Whether it describes the real cosmos remains even now an open and beautiful question. In the early years of the last century, a young patent clerk named Albert Einstein finished a set of equations that would quietly rewrite the meaning of space and time. These equations did not treat space as an empty stage. They treated it as something living, something that could stretch, curve, and bend under the weight of matter and energy. Space was no longer the silent room in which stars were placed. Space itself became part of the music. When Einstein looked at his own work, he noticed something strange. The equations did not want to sit still. They suggested a universe that must either be growing or shrinking, never quite resting. This troubled him. Like most thinkers of his day, he assumed the cosmos was eternal and unchanging, a great still ocean of stars. So he added a small term to his equations, a kind of gentle push to hold the universe steady. He later called this his greatest mistake. But hidden inside that mistake was a beautiful idea. If the universe could be balanced like a held breath, then perhaps it could also exhale. Perhaps it could expand, slow, and pull itself back in. Perhaps it could breathe. The Russian mathematician Alexander Friedman took Einstein's equations and asked what would happen if you let them move freely. He found 3 possible cosmoses. One would expand forever, thinning out into endless cold. One would expand just barely, slowing toward a quiet stillness. And one would expand, stop, and fall back inward, collapsing under its own gravity. That third possibility is the one that quietly haunts our story tonight. A universe that rises and falls. A universe that might, perhaps, do so again and again. What would such a universe be made of? The same things our universe is made of, only pressed and stretched in different ways through each cycle. Hydrogen and helium, the 2 lightest elements, forged in the first few minutes after a hot, dense beginning. Heavier elements brewed slowly inside stars over billions of years. Carbon, oxygen, nitrogen, iron, the very atoms in your fingertips, were once buried in the cores of stars that lived and died before our sun was born. Think of the iron in your blood. It was made in the heart of a massive star, then thrown across space when that star exploded. The calcium in your bones was forged the same way. The gold on a wedding band may have come from the collision of two neutron stars, those dense remnants left behind when giants die. Every heavy atom in your body carries the signature of older worlds. Water, too, has a long story. Some of it may have formed in cold clouds of gas and dust long before the Earth existed. Some may have arrived on icy comets and asteroids that struck the young planet. The ocean you have stood beside is, in part, a gift from the deep cold of space. Each drop carries hydrogen made in the first minutes of the cosmos, and oxygen forged later inside dying stars. Now hold all of this in mind and ask the soft question at the center of tonight's wondering. If the universe truly breathes, if it expands and contracts in long, slow beats, then where did these ingredients come from at the start of our cycle? Were they freshly made in our own Big Bang, or were some of them passed forward from a cycle before? Most physicists who study cyclic models believe each bounce resets the material, almost entirely, melting everything back into pure energy. But a few wonder whether faint traces, patterns, or imprints might survive the crossing. The question remains open. Einstein himself never embraced the bouncing cosmos. He removed his correction term once he learned the universe was expanding, and he moved on to other puzzles. But the door he opened never closed. Friedman's equations still allow for a closed universe that could fall back on itself. Whether the real cosmos chose that path depends on the total amount of matter and energy it contains, and on the strange pressure of what we now call dark energy. We are not yet sure of the answer. For tonight, picture the cosmos as Einstein once briefly imagined it. A great soft sphere of space, gently breathing. Stars are born inside it from clouds of hydrogen. Planets gather from rocky dust, oceans pool on cooling worlds. Living things rise on at least one of those worlds and look up at the sky and ask where it all began. And the answer, perhaps, is that it did not quite begin. It only turned once again toward the light. To imagine a universe that bounces, we first have to imagine the forces that might bring it back. Gravity is the oldest of these, the quiet, patient pull that every speck of matter feels for every other speck. It does not push. It does not announce itself. It simply gathers gently across distances so wide that light itself grows weary crossing them. For most of the 20th century, physicists thought that gravity might win. They pictured all the galaxies slowing in their flight, pausing, and then beginning to fall back toward one another in a long, soft return. That return had a name. They called it the Big Crunch. In this picture, the expansion that began with the Big Bang would eventually run out of breath. Gravity would take over. Galaxies would drift closer. Space itself would shrink. Temperatures would climb as the cosmos compressed until everything we know folded back into a single hot point. And then, perhaps, that point would bounce and a new universe would unfurl from the ashes of the old. It was a tidy idea. It gave the cosmos a heartbeat. It allowed the universe to be both ancient and renewed. But nature, as it often does, gave us a surprise. In the late 1990s, astronomers studying distant exploding stars noticed something strange. The far galaxies were not slowing down. They were speeding up. Some unseen pressure was pushing the cosmos apart, faster and faster. We gave that pressure a placeholder name. We called it dark energy because we did not, and still do not, know what it truly is. Dark energy changes the story of the crunch in a deep way. If this pushing force keeps its current strength, gravity will never catch up. The galaxies will simply drift farther and farther until each one is alone in its own dark pocket of space. No crunch, no bounce, just an endless cooling stretch. The cyclic universe, in this version of the future, has nowhere to begin again, and yet the question stays open. We do not know what dark energy is. We do not know if it is constant or if it changes over time. Some researchers wonder whether it could weaken in the far future, allowing gravity to slowly reassert its old authority. Others wonder whether it might strengthen, tearing space apart in a different kind of ending. Both possibilities sit on the table, and neither has been ruled out. This is where cyclic models become interesting again. Some of them do not need a crunch at all. They imagine that the bounce happens not because the universe collapses, but because the very fabric of space passes through a kind of phase change. Pressure, in these models, is not just a force pressing matter together. It is a property of empty space itself, and it can flip its sign. What pulls apart in one era can pull together in the next, or, perhaps stranger still, the bounce might happen in a deeper dimension we cannot see, with our familiar 3 dimensions only feeling the gentle echo of a much larger event. Heat plays its part too. In the early universe, temperatures were so extreme that the forces we now treat as separate were once a single force. As the cosmos cooled, those forces split apart, like ice crystals forming in still water. If a cyclic universe truly exists, then every bounce would have to repeat this cooling, this slow sorting of forces, again and again. Some theorists wonder whether each cycle would cool the same way, or whether tiny differences would accumulate, giving each new universe slightly different laws. Radiation, the leftover glow of an earlier hot age, is another quiet sculptor. It once filled space with such fierce light that atoms could not even hold themselves together. As the cosmos expanded, that radiation stretched and dimmed, until today it is only a faint whisper of microwaves. In a cyclic model, this whisper would be the fingerprint of the last beat, and the question becomes whether anything from before could have left a mark inside it. So we sit with several forces, each pulling the story in a different direction. Gravity, the gentle gatherer. Dark energy, the unknown pusher. Heat and radiation, shaping the texture of space as it cools. We do not know which of these will write the final chapter, or whether there even is a final chapter. The crunch may come, the crunch may never come. The bounce may happen in a place we cannot see, governed by rules we have not yet imagined. For now, the forces continue their slow work, and the universe keeps drifting outward, quietly, while we watch and wonder. All around us, in every direction we point a sensitive antenna. A soft glow is falling on the earth. It is not light our eyes can see. It is a faint hiss of microwaves, cold and gentle, arriving from the most distant horizon of space. We call it the cosmic microwave background. It is the oldest light in creation, set free when the young universe first cooled enough to let light travel freely. And inside that ancient glow, some thinkers suspect, may lie the faintest fingerprints of a cycle that came before our own. To feel the scale of this glow, try to picture its temperature. The whole sky shines at about 2.7 degrees above absolute zero. That is colder than any winter night on Earth, colder than the surface of Pluto, colder than the dark side of an icy moon drifting at the edge of our solar system. If you could stand inside the deepest cave on the deepest planet of the farthest star, you would still be bathed in this gentle warmth. It is the leftover heat of the entire cosmos, smoothed and stretched across 13 billion years. The light itself began its journey when the universe was only about 380,000 years old. That sounds like a long time, But compare it to the universe today, which is roughly 13.8 billion years old. If you scaled the full life of the cosmos to a single year, that early moment would land in the first 20 minutes of January 1st. The microwave background is a baby photograph taken before the first star ever lit up, before the first galaxy ever spun into shape. The temperature is almost the same in every direction, almost. The tiny ripples on top of that smoothness are unbelievably small. If the average glow were the height of a calm ocean, the ripples would be smaller than the thickness of a human hair laid across that ocean. 1 part in 100,000. That is the precision we are talking about. And yet, inside those whisper-thin ripples, scientists have read the story of how galaxies later grew, how matter clumped, how the early seeds of structure first took hold. Now imagine looking for something even fainter, something even more delicate. Some researchers have wondered whether a previous cycle of the universe, if such a thing existed, might have left scars or rings or soft circular patterns inside that already whisper-thin pattern. We are talking about a signal hidden inside a signal hidden inside a signal. A pebble dropped into a pond generations of universes ago, whose last gentle ripple might still be crossing our sky tonight. To feel how small such a hint would be, picture a single grain of fine sand placed somewhere on a beach that stretches the length of an entire continent. Now picture trying to find that grain by feeling the beach with your bare hand. That is roughly the kind of search some cosmologists are attempting. They scan the all-sky maps gathered by orbiting telescopes, looking for shapes that no ordinary model predicts. Faint rings, cold spots, soft alignments that might, just might, carry information from before the bang. Other researchers see the same maps and find nothing unusual at all. They argue that the patterns claimed as relics are simply what you get when you stare long enough at random noise. Our eyes and our computers love to find shapes. The human mind sees faces in clouds. Statistics, they say, will always offer up a few odd rings if you look hard enough. So far, no claimed echo has been confirmed by every team that has examined it. The question remains open. Hold the scale in your mind for a moment longer. The observable universe stretches about 93 billion light-years across. That is the width of the bubble we can, in principle, ever see. Yet the entire cosmic microwave background, this faint warm bath that fills all of that space, carries a total energy so small that if you collected every microwave photon striking the Earth in a year, you could power a single small light bulb for only the briefest flicker. The signal is enormous in reach and almost nothing in strength, and the proposed signature of a prior cycle would be a tiny twist inside that already gentle whisper. Whether any such echo truly exists, we do not yet know. The instruments grow more sensitive each decade. The maps grow sharper. The patience of the searchers grows deeper. For now, the oldest light in the sky keeps falling on us quietly, carrying either the simple story of one beginning, or perhaps the soft, almost erased memory of many. Imagine you could float somehow at the moment of the bounce, not before the Big Bang and not after it, but inside the strange scene where one possible cycle might pass into the next. What would you see? The honest answer is that no one knows, but the theories give us pictures, and the pictures are worth sitting with for a while. In the old singular Big Bang model, there is no surface to stand on. There is only a single point of infinite density, a place where every law of physics gives up and falls silent. The math simply stops working. You cannot draw it. You cannot picture it. It is a wall the equations cannot climb over. Bounce models try to replace that wall with something gentler. In loop quantum cosmology, one of the leading bounce ideas, space itself is not smooth. Space is made of tiny woven threads, finer than any atom, almost like a fabric stitched from the smallest possible stitches. As the old universe falls inward and grows denser, these threads cannot be packed any tighter. Space pushes back, the crush slows, the crush stops, and then, very gently in the math, space begins to expand again. If you could float near that moment, what might you see? Some theorists picture a glowing ocean of pure energy, dense beyond anything our sun could imagine, yet strangely smooth. The colors would not be colors as we know them. Light at that density blends into a uniform white-hot haze, with no shadows, no edges, no above and no below. There is no terrain because there is no room for terrain. Every direction looks the same. Every direction is the same. Other researchers picture the bounce differently in the ekpyrotic models, which we will visit more closely in the next section. The surface of the bounce is not a smooth haze, but a kind of collision shock, like the moment two vast sheets meet and ring against each other. The energy would pour out along the meeting place in waves, and the new universe would inherit its first heat from that ringing. Penrose's conformal cyclic idea paints yet another picture. In his vision, the surface between aeons is not a violent crush at all. It is a soft handoff. The old universe, after almost infinite ages of cooling and thinning, forgets what size it ever was. Size loses meaning. The cold, empty, ancient cosmos and the hot, dense, newborn one become mathematically interchangeable. The surface, if you could find it, would be less a wall and more a translation, where one language quietly becomes another. Each of these pictures is a guess. Each rests on math that works in some places and breaks in others. None of them has been confirmed. The bounce, if it happened, left no postcard for us to read. Standing at this imagined surface, you would also lose your sense of time. In every bounce model, the familiar arrow that points from past to future grows confused near the crossover, cause and effect bend. The notion of before and after softens. Some physicists wonder whether time itself pauses in the deepest moment of the bounce, holding its breath between two heartbeats of the cosmos. Others think time keeps flowing, but in a form so unfamiliar that our clocks would not recognize it. The textures of this surface, if textures even exist there, would be quantum textures, not rock, not gas, not plasma in the ordinary sense, more like a shimmer of possibilities, each pocket of space trying out different futures at once, before settling into the one that will become our familiar cosmos. Picture a wide silver sheet rippling everywhere at once, with each ripple containing the seed of a galaxy that will not exist for another billion years. We should be honest though, we have no telescope that can see this surface. We have no instrument that can press into it. Even the cosmic background glow, which we will return to later, only shows us a much later moment, long after any bounce would have finished. The surface of the bounce is hidden behind a curtain of light we cannot lift, so the pictures stay as pictures, a smooth white ocean, a ringing collision, a soft conformal handoff, three very different surfaces for three very different theories, each describing the same imagined moment in a different language. Which one, if any, matches what really happened remains an open question. Maybe none of them is right. Maybe the truth is stranger than all three. For tonight, you can simply hold the image of that bright, quiet, impossible surface in your mind. The place where the universe might have stopped falling, paused, and started rising again. The seam, if there is one, between what was and what is. beneath the calm surface of our night sky. Beneath the steady glow of distant galaxies, some physicists picture something stranger than any star. They picture sheets, vast, silent sheets of space, stretched across a hidden dimension we cannot see. In their picture, our entire universe, every galaxy, every grain of dust, every breath you have ever taken, sits on one of these sheets, and, somewhere nearby, separated by a gap so small it borders on the imaginary, another sheet drifts in parallel. These sheets are called branes, short for membranes. The idea grew out of string theory, the long search for a deeper layer of physics beneath particles and fields. In that search, some thinkers began to wonder whether what we call space might itself be a kind of surface floating inside a higher space we have no access to. If that is true, then our 3 dimensions of length, width, and height might be only one slice of something larger, a slice we can never step off of, no matter how far we travel. From this picture grew a model called the ekpyrotic scenario, a name borrowed from an old Greek word meaning out of fire. In this model, the Big Bang was not the beginning of everything. It was a collision, 2 branes, drifting slowly through the hidden dimension between them, drew together and touched. The moment of contact released a flood of energy across both surfaces. That flood, on our brain, became the hot, dense soup we now call the early universe. The picture is gentle and strange at once. Imagine 2 enormous flat sheets of silk hanging in a dark room, almost still, almost touching. They sway by fractions of nothing. Across millions or billions of years, they drift closer. When they finally meet, every point on both sheets meets every other point at the same instant. There is no center to the collision, because the collision happens everywhere at once. That, the model suggests, is why our universe looks the same in every direction we point a telescope. After the kiss, the branes drift apart again. They begin a slow, patient cycle. The energy of the collision cools and spreads. Galaxies form, stars ignite, burn, fade, and across timescales we can barely write down, the branes prepare for another meeting. Each cycle leaves the larger structure mostly unchanged. Only the surfaces themselves remember the touch. This is one possibility. It is not the only one, and it is far from proven. Many physicists are deeply skeptical. The ekpyrotic model depends on extra dimensions that have never been detected, and on a version of string theory whose details remain unsettled. The mathematics is delicate. Small changes in the assumed shape of the hidden dimension can change the predicted outcome completely. Critics argue that the model has too many free parts, too many knobs to turn, and not enough sharp predictions we could test from inside our own brain. The competing view is the more familiar one. In standard inflationary cosmology, the early universe stretched itself smooth in a fast burst of expansion. Right after the Big Bang, there are no branes, no hidden sheets, no collisions, just one beginning and one long unfolding. Inflation has its own puzzles, but it fits much of the data we have gathered from the cosmic background glow. Many researchers prefer it for that reason. Others find it unsatisfying, because it asks us to accept a special starting condition without explaining where that condition came from. The ekpyrotic picture offers a different kind of comfort. It replaces a single mysterious beginning with a repeating event, something that happens again and again, the way tides return to a shore. But it cannot yet show us the shore. Any signal from a previous collision would have to survive the violence of the next one, and travel across a structure we have no way to probe. Whether such a signal could even exist is part of what remains unknown. So we are left with 2 sheets we cannot see, drifting through a dimension we cannot enter, possibly preparing for another touch we will never witness. The idea is quiet, almost peaceful, when you sit with it. A cosmos not born once in a flash, but rocked gently between two surfaces forever. Or perhaps not. Perhaps the Branes are only a beautiful story, and our universe really did begin once and only once. Either way, the question stays open. The Branes, if they exist, do not announce themselves. They drift in their slow silence beneath everything we can measure. And tonight, as you rest, they may already be moving, patient, invisible, gathering toward the next quiet kiss that begins another world. Everything in the cosmos seems to move in cycles. The Earth turns on its axis, and day becomes night. The moon pulls the seas in slow breaths we call tides. Stars rise, burn for ages, and then drift into colder forms. Even the great clouds of gas between the stars collapse, ignite, scatter, and gather again over spans we can barely picture. So it is not strange that thinkers have wondered whether the universe itself might breathe in the same way, on a scale so vast that one full breath could swallow every story ever told. If the cosmos is cyclic, what would its rhythm feel like from the inside? We would never sense the larger pulse. A single beat could last trillions of years, far longer than any star, far longer than any galaxy holds its shape. From within one beat, the universe would seem to simply expand. Galaxies would drift apart, light would stretch and redden. Space itself would grow colder and quieter, like a room slowly emptying of sound. That slow stretch toward cold and quiet is the part we can actually study. Our own cycle, if it is a cycle, appears to be in its long exhale. The universe is not just expanding, it is expanding faster than it did a few billion years ago. Some unseen pressure, which we call dark energy, is pushing the great web of galaxies apart. Whether that pressure stays steady, fades, or grows is one of the deepest open questions in physics. The shape of the next many billion years depends on which answer is true. In one picture, the exhale never stops. Galaxies wander farther. Stars finish their fuel. The last red dwarfs flicker out after trillions of years. Black holes themselves slowly evaporate across timescales, so long they make the present age of the cosmos seem like a single heartbeat. The universe drifts into a near-perfect stillness, an ocean of cold photons and lonely particles spread across unimaginable distance. In some cyclic models, this stillness is not the end. It is the hush before the next beat. In a competing picture, the exhale eventually reverses. Gravity, or some hidden field, slows the expansion, halts it, and pulls everything back inward. Galaxies that took billions of years to separate would fall toward one another again. The cosmic background light would heat. As space contracts, the night sky would brighten, not from new stars, but from compression itself. This was the old oscillating dream, and most observations now make a simple return collapse look unlikely. Yet softer versions of the idea remain alive, where a quiet phase ends in a gentle bounce rather than a crushing fall. The rhythms inside a cycle would not be uniform. Each phase carries its own character. There is the hot, dense opening, where particles flood into being and light cannot travel freely. There is the long, bright middle, when galaxies form and stars sculpt heavy elements in their cores. There is the slow fading, when star formation slows and the night grows deeper. And then, perhaps, the bounce, or the kiss of Branes, or the transition Penrose imagines, where the very meaning of size and time loosens enough to begin again. What sets the tempo of these movements? In some models, it is the behavior of a single field that fills all of space swinging slowly between values like a pendulum spanning eternity. In others, it is the geometry of higher dimensions we cannot see. In loop quantum cosmology, it is the granular nature of space itself, which refuses to be crushed past a certain density and rebounds. Each idea writes a different score for the same long song. None of them has been confirmed. The strangest thing about a cosmic cycle is how invisible its rhythm would be to anyone living inside it. A creature in the middle of an exhale would see only expansion. A creature near a bounce would see only chaos. Only by piecing together faint clues across the whole sky could observers ever guess at the larger pattern. And those clues, if they exist, would be very gentle. A slight twist in the cosmic background, a faint ring of warmth where none should be, a tiny tug on the way galaxies cluster. So far, none of these whispers has been confirmed as a true echo of a prior cycle. Some researchers see hints, others see noise. The honest answer is that we are still listening, still learning what to listen for. The universe may be breathing on a scale we can barely begin to measure, or it may have taken only one breath very long ago and be slowly letting it go. For now, we sit inside the slow stretch, watching the light grow colder, wondering whether this quiet is an ending or the long pause before another beginning. There is an idea that sits beside the bouncing universe, like a quiet neighbor. It does not look quite the same. It does not move quite the same, but it shares a fence with the cyclic models, and the two often whisper to each other across that fence. This idea has a long name. It is called Conformal Cyclic Cosmology. The mathematician Roger Penrose proposed it, and it offers a strange and lovely picture of how one universe might pass into another. The picture goes something like this. Imagine our cosmos expanding for a very, very long time. Stars burn out, galaxies drift apart, black holes swallow what is left, and then slowly evaporate over almost unthinkable spans of time. After enough time, nothing remains but a thin, cold soup of light. No matter, no clocks, no rulers, just photons drifting in a quiet dark. Here is where the idea turns gentle and strange. When there are no masses left in the universe, there is nothing to measure size with, nothing to mark time. And in that empty state, a very large, cold cosmos starts to look mathematically like a very small, hot one. The huge and the tiny become hard to tell apart. Penrose suggested that this similarity is not just a trick of the math. He suggested that the cold, empty end of our universe could become the hot, dense beginning of the next. Each full life of a universe, in this view, is called an Aeon. Our Big Bang would be the start of our Aeon. Long before it, another Aeon lived its full, slow life, and after hours fades into the dark, another Aeon will quietly begin. There is no crunch, there is no rebound. The transition is smooth, almost dreamlike, because the two states are mathematically similar when nothing remains to give them scale. This is very different from the bouncing models in earlier sections. A bouncing universe collapses and then expands again, like a chest rising and falling. Penrose's universe never collapses. It just stretches forever, forgets its size, and slips into a fresh beginning. Both pictures give us cycles. Both refuse to grant a single first moment, but they reach those cycles by very different roads, and most cosmologists are not convinced by either one. The conformal idea has its critics, and the criticisms are serious. For the transition to work, every particle with mass must eventually decay or fall into a black hole. Electrons, for example, are stubborn. As far as we can tell, they do not decay. If they last forever, then the universe never reaches the timeless scalar state the theory needs. Penrose has suggested that perhaps the electron's mass slowly fades over enormous time. Other physicists find this too steep a price to pay. The question remains open. There is also the matter of evidence. Penrose and a few collaborators have searched the cosmic microwave background, the faint glow left over from the early universe, for circular patterns they call Hawking points. These are spots where, they argue, the evaporation of a black hole from a previous Aeon may have left a soft, warm ring in our own sky. Some researchers have reported finding such patterns. Others have looked at the same data and found nothing unusual at all. The signals, if they exist, are very subtle. They sit at the edge of what our instruments can see. So the neighbors here are two cosmologies that share a dream and disagree on the mechanism. The bouncing models say the universe presses itself together and then pushes back out. The conformal model says the universe simply forgets itself and starts again from emptiness. One imagines a heartbeat. The other imagines a long, soft exhale that somehow becomes a new inhale, with no clear boundary between them. What both ideas share is a refusal to treat the Big Bang as the true beginning. Both place our cosmos inside a longer story. Both suggest that something came before, even if that something has been almost entirely erased. And both struggle with the same difficulty. How could any whisper from a previous Aeon or a previous bounce reach us through whatever transition lies between? The conformal model says the whisper might come as faint rings in the background light. The bouncing models suggest other clues, which we will sit with in later sections. For now, it is enough to picture two quiet neighbors leaning over the same fence, looking at the same dark sky, telling slightly different stories about what lies on the other side. Neither has been proven, neither has been ruled out. The mystery stretches in both directions, patient and unhurried, waiting for us to look more closely when we are ready. If a universe could remember, what would it remember of the one before it? This is the strange question that pulls us into the most extreme corner of cyclic cosmology. Not whether bouncing universes exist, but whether any trace of a former cosmos could survive the violent narrows of a bounce and arrive on the other side, faint and battered, in the cycle we now call home. Think about what a bounce would have to be. In most cyclic models, the universe shrinks down toward a state so dense and so hot that ordinary matter loses all meaning. Atoms dissolve, nuclei dissolve. Even the smooth fabric of space and time begins to tremble. Then, somehow, this almost unimaginable density rebounds. The exact moment of the bounce is the hottest, smallest, most extreme event a universe can ever undergo, and anything that wanted to carry a message from one cycle to the next would have to ride straight through that fire. So the question becomes a question about extremes. What kind of signal could possibly be that tough? One candidate, suggested by Roger Penrose, is gravitational waves, ripples in the shape of space itself, made by the most violent events in any cosmos. In his picture, the colossal collisions of giant black holes near the end of a previous Aeon would stamp faint, ring-like patterns into the leftover light of our own early universe. These patterns are sometimes called Hawking points, after the late physicist who helped imagine them. They would be the coldest, oldest fingerprints we could ever find. A few researchers say they see hints of such rings in the cosmic microwave background. Many others look at the same data and see nothing but the ordinary speckle of random noise. The debate remains open, and the evidence is gentle, not loud. A second candidate is even stranger. In some bounce models, tiny black holes formed in the previous cycle might survive the crossing entirely. They would be the rarest kind of relic. small, dense knots of warped space, far older than our Big Bang, drifting through the new cosmos like seeds from a forgotten orchard. No such object has ever been confirmed, but the idea sits on the table, quietly waiting for a telescope sensitive enough to test it. Then there are the more abstract possibilities. Loop quantum cosmology, which replaces the singularity with a quantum bounce, suggests that the smoothness of space itself might carry a kind of prehistory. The bounce would not erase everything. Certain large-scale features in the distribution of galaxies, or certain twists in the polarized light of the early sky, might reflect conditions set before our cycle began. These would be the deepest signals of all, written not in matter, but in the geometry of the cosmos itself. Yet, for every hopeful idea, there is a sober counter-voice. Many cosmologists argue that the bounce, whatever its precise nature, should be a near-perfect eraser. The temperatures involved are so extreme, the densities so enormous, that information from a previous cycle should be smoothed away into uniform heat. In this view, each new universe wakes up with amnesia. The slate is clean. The mystery of what came before is not just unsolved, it is permanently sealed. Both views agree on one thing. The bounce, if it happens, is the most extreme physical event imaginable. It is hotter than any star, denser than any black hole interior we can describe, smaller than any volume we can measure. It is the place where the equations we trust begin to whisper that they are no longer enough. Whether memory can survive such a passage is a question about the limits of physics itself. There is something soothing in this. The most extreme event a universe can have, in cyclic models, is not a beginning out of nothing. It is a transition, a fierce, narrow gate between one cosmos and another. And the question of what passes through that gate, if anything, is one of the oldest and quietest puzzles in modern cosmology. The hottest moment, the coldest aftermath, the longest possible history, all wrapped together in a single uncertain instant. We do not know if our cosmos remembers. We do not know if the faint patterns some researchers point to in the microwave sky are echoes or illusions. We do not know if loops, branes, or aeons describe anything real. The data is sparse. The theories are many. The bounce, if it exists, hides most of its secrets behind a wall of heat we cannot yet see past. For tonight, let the thought settle. Somewhere in the deep background of the sky, there may be a memory, or there may be only the calm static of a beginning that began with nothing to remember at all. There is a quiet rule in physics, softer than gravity, gentler than light, yet somehow more stubborn than either. We call it the second law of thermodynamics, and it says something very simple. Disorder tends to grow. A warm cup of tea cools. A sandcastle crumbles. A star, given enough time, scatters its heat into the cold dark around it. This slow drift from order toward disorder gives us what we feel as the arrow of time. It is the reason yesterday cannot be unscrambled. It is the reason we remember the past and not the future. For a universe that bounces, this gentle rule becomes a very large problem. If each cycle inherits the disorder of the one before, and the bounces should pile up like dust in an old attic, after countless cycles, the universe would be drowning in entropy. It would be a sea of lukewarm noise, with no room for stars to form or galaxies to gather. Yet our cosmos, the one we can see, looks startlingly fresh. It glows. It clusters. It still has work left to do. So, if there were cycles before ours, something must have wiped the slate, or stretched the disorder thin, or hidden it somewhere we cannot find. The classical bouncing models of the 20th century struggled here. Each crunch, each rebirth would compress all the leftover heat and chaos of the previous cosmos into the next. Like folding a blanket of static again and again, the noise would only grow. This was one of the quiet reasons many physicists set the idea aside. The math was tidy, the picture was beautiful, the bookkeeping of disorder simply would not balance. Modern cyclic ideas try to solve this in different and rather lovely ways. In the ekpyrotic picture, the universe between bounces stretches enormously before the next collision. That long, slow stretching dilutes the disorder, the way a single drop of ink fades in a vast lake. By the time the next bounce arrives, the entropy density is small again. The total disorder still grows, but each new region of space starts out clean and smooth, with room to build new structure. Penrose's conformal cyclic cosmology takes an even stranger path. In its picture, the far, far future of the universe loses track of size altogether. When only photons remain, and photons do not carry clocks or rulers, the cosmos forgets how big it is. The huge, cold, disordered end becomes mathematically the same as the tiny, smooth beginning of the next aeon. Entropy, in this view, is not erased, it is simply rescaled until it no longer matters. Whether this trick is physically real or only a clever piece of geometry remains very much an open question. Loop quantum cosmology offers a third whisper. There, the bounce happens because space itself is grainy at the smallest scales. When matter is squeezed enough, the grains push back and the crunch becomes a rebound. Some versions of this model suggest the disorder of the prior cycle could leave faint patterns in the new one, like wrinkles, ironed almost flat. Others suggest the bounce scrambles things so thoroughly that the next universe truly does begin fresh. The mathematics is still being worked out, and reasonable researchers disagree. The deeper puzzle is why our own early universe was so orderly to begin with. The cosmic background glow shows a young cosmos, but was astonishingly smooth and cool in the right way. Its entropy was strangely low for something so hot. This low starting point is what gave time its arrow, what allowed stars to ignite and clocks to tick forward. No one fully understands why the universe began in such a tidy state. Some thinkers say it was simply a lucky initial condition. Others believe it is a clue, a fingerprint left by whatever came before, if cycles are real. The question becomes whether each new universe must somehow reset its entropy, or whether the arrow of time itself flips, or whether disorder is quietly carried into hidden dimensions we cannot see. Each answer brings its own strange beauty. Each one is still, in the most honest sense, a guess dressed in equations. So tonight, as you rest, picture this small and stubborn fact. The universe leans, always, toward disorder. And yet, here we are, in a cosmos still rich with shape and light. Somewhere in that contrast lies a clue. It might be the clue that tells us whether time began with our bang, or whether it has always been ticking, cycle after cycle, with some gentle hand smoothing the sheets between each bed of stars. We do not know which. We may not know for a long while. The arrow points forward, and we follow it, wondering. The story of how humans came to imagine a universe with no first moment is, in its own quiet way, a story of giving up. For most of the 20th century, physicists chased the singularity. They followed the math of general relativity backward in time, and the math kept pointing to a single instant where everything, space, time, matter, light, collapsed into a point of infinite density. A place where the equation simply stopped working. For decades, that broken point was treated as the beginning. the edge of the map, the wall beyond which no question could be asked. Then slowly, a small group of physicists began to wonder if the wall was real or only an illusion of the math. The trouble, they suspected, lay in mixing two beautiful theories that refused to speak to each other. General relativity describes the smooth bending of space on enormous scales. Quantum mechanics describes the tiny, jittery world of particles and fields. Near the singularity, both theories matter at once, and neither one alone can tell the whole story. The singularity, in this view, is not a true beginning. It is a sign that our tools have run out. In the 1980s and 1990s, a quieter branch of physics began to take shape. It was called loop quantum gravity. Its goal was to rebuild space and time from the smallest possible pieces, tiny loops of geometry woven together like a fabric seen too close to be smooth. In this picture, space is not a continuous sheet, it is grainy. There is a smallest possible volume, a smallest possible length below that scale. The idea of smaller simply does not apply. A handful of researchers, among them Martin Bogerwald, working in the early 2000s, began applying these ideas to the universe as a whole. They asked a strange and patient question: what happens to the equations of cosmology when space itself cannot be squeezed below a certain size? The answer that emerged was quietly astonishing. The singularity disappeared. In its place, the equations described a bounce. The universe, contracting under its own gravity, reaches a tiny but finite size. Then, pushed back by quantum effects, it expands again. This framework came to be called loop quantum cosmology. In its simplest form, it suggests that what we call the Big Bang was not a beginning, but a hinge, a turning point between a contracting cosmos and an expanding one. On the other side of that hinge, there could have been another universe, perhaps much like ours, perhaps very different, collapsing toward the same narrow gate we burst out of. The history of this idea is not the history of a single eureka moment. It is the history of small papers, careful calculations, and long arguments at chalkboards. Researchers built simplified models of the universe, stripped down to their barest essentials, and asked the equations what they did near the bounce. Again and again, the math gave back the same gentle answer: no infinity, no wall, just a smooth handoff from one phase to another. Other physicists remained unconvinced, and they still are. The simplified models, critics point out, leave out many real features of the universe. Adding those features back in might restore the singularity, or it might produce something stranger still. The full theory of loop quantum gravity itself is incomplete. No one has yet shown, with full rigor, that the bounce survives in a more realistic setting. The idea is beautiful, but it lives on careful scaffolding that has not yet been tested. There were instruments in this story too, though they were not telescopes or particle colliders. They were computers, slowly grinding through equations that no human could solve by hand. They were the long traditions of mathematical physics, passed from teacher to student, and there were mistakes. Early models that gave the wrong answers, assumptions that had to be quietly retired, hopeful predictions that did not survive closer inspection. What makes this chapter of the story so different from earlier discoveries is that no one has yet seen the bounce. No image has been taken, no signal has been confirmed. The bounce, for now, lives only in equations. It is a possibility carved out by mathematics, waiting for some future observation to either support it or rule it out. Some researchers hope that subtle fingerprints in the cosmic microwave background might one day distinguish a bounce from a true beginning. Others suspect that such fingerprints, if they exist, would be too faint to ever measure. So this is the strange place we have arrived. The history of discovering the bounce is not yet finished. It is a discovery still being made, quietly, slowly, by people who chose to question the wall and ask what lay beyond it. Among the strangest ideas in modern cosmology is the thought that our universe might have a twin, not a copy floating somewhere else in space, but a mirror cosmos running in the opposite direction of time. Some physicists have wondered whether the moment we call the Big Bang was not really a beginning at all, but a kind of pivot point. On one side of that pivot, time flows the way we know it. On the other side, time flows the other way, and a whole second universe unfolds backward from ours. This idea sounds like something from a dream, but it grew from a serious attempt to solve a puzzle. The puzzle is the arrow of time. Why does time only go forward for us? Why do broken cups never reassemble themselves? Most laws of physics work just as well in reverse, so the forward flow of time is not built into the equations. It seems to be built into the conditions at the Big Bang. A small group of researchers has suggested that those conditions might have produced two universes at once. Picture an hourglass laid on its side. The narrow waist is the Big Bang. To the right, our cosmos expands, cools, and ages. To the left, another cosmos expands in its own direction of time, with its own galaxies, its own stars, its own slow march toward whatever end awaits it. From inside either side, the other side looks like the deep past. From the outside, if such a view were possible, the two would look like reflections in a still pond. This proposal does not claim that the mirror cosmos is reachable. It is not a place you could travel to. The two halves share only that single moment at the center, the pivot itself. After that, they drift apart in opposite temporal directions and never meet again. Whether anything in the mirror cosmos could be called real in the same way our universe is real remains an open question. The mirror idea connects in a curious way to the cyclic picture. If the Big Bang can give birth to two universes pointing away from each other in time, then perhaps a bounce can do something similar. Perhaps every contraction and re-expansion produces not one new cosmos, but a pair, each unaware of the other. Some thinkers find this elegant, others find it troubling. There is no observation yet that can settle the matter. A competing view holds that the arrow of time has a simpler source. In this view, the early universe was simply in a very low entropy state, a state of unusual smoothness and order. Everything that has happened since is the slow unwinding of that order. No mirror cosmos is needed. The forward flow of time is just the natural drift from low disorder to high disorder, and the Big Bang was a single event with a single direction. This explanation is older and more accepted, but it does not fully answer why the early state was so orderly in the first place. There is another surprise tucked inside the mirror picture. In some versions of the idea, certain particles in our universe could have partners on the other side. These partners would be hidden from us by the pivot itself. They would carry their own properties, their own behaviors, perhaps even their own forms of matter that do not interact with ours at all. Some researchers have wondered whether dark matter, the unseen stuff that holds galaxies together, could be related to such hidden partners. This is a deeply speculative thought. Most physicists do not endorse it, but it shows how a single strange idea can ripple outward into other unsolved puzzles. What makes the mirror cosmos so unsettling and so beautiful is that it asks us to give up the feeling of being the only universe born from our Big Bang. It suggests that the moment of our origin may have been a doorway with two sides, and we happen to live on one of them. If cyclic models are correct, then perhaps every cycle has its own pair of mirrored universes, and the full history of existence is even larger and stranger than the simple loop suggests. For now, the mirror cosmos remains a thought experiment. There is no signal we have caught from the other side. There is no way yet to test whether the pivot exists at all. The arrow of time stays one of the deepest unsolved puzzles in physics, and the question of whether it points only forward or also backward into a hidden twin sits quietly among the other open questions of the cosmos, waiting for someone to find a way to ask it more carefully. There is a strange and beautiful idea that hides at the meeting point of two great mysteries. One mystery is what happens inside a black hole, where matter falls in and is crushed beyond our understanding. The other mystery is what happened at the very start of our universe, when everything we see was packed into something unimaginably small. Both involve a singularity, a place where the math we trust simply stops working. And some physicists wonder if these two mysteries might be the same mystery seen from opposite sides. The thought goes something like this. When a star collapses and forms a black hole, matter inside it falls toward a single point. In standard physics, that point has no size and infinite density. But some researchers suspect that nature does not actually allow such a point to form. Instead, the falling matter might reach a limit, bounce, and begin to expand again. From the outside, we still see a black hole. From the inside, a brand new region of space might be unfolding, a baby universe hidden behind the horizon. This idea is not proven. It is one possibility among several, but it offers a tempting bridge. Our own Big Bang could have been such a bounce. Viewed from within, the black hole of some older, larger cosmos may have given birth to everything we know, and inside the black holes of our own sky, new cosmoses may be quietly blooming, sealed away from us by their horizons. Other physicists are skeptical. They point out that we have no direct evidence for any of this. The interior of a black hole is the most hidden place in nature. Nothing that falls in can send a signal back out. So the idea of black holes as seeds of new worlds may be untestable in principle. A competing view holds that singularities are real, that information ends there, and that nothing new begins on the other side. The debate sits unresolved. What makes the idea compelling is how it links systems across vastly different scales. A dying star, collapsing in one corner of one galaxy, might echo the birth of an entire cosmos. The death of one thing becomes the cradle of another. In this picture, the universe is not a single chamber, but a kind of branching tree, with each black hole sprouting a new branch. Some thinkers have even imagined a slow evolution across generations of universes, where the ones that produce more black holes produce more children, and the laws of physics themselves drift toward whatever settings make black holes most common. This is a speculative idea, sometimes called cosmological natural selection. It is not widely accepted. Critics note that we cannot yet check whether our universe really is fine-tuned for black hole production, and that the analogy with biological evolution may not hold. Still, the idea shows how the small and the large might be woven together. A collapsing star is not just a local event, it might be a seed. Cyclic cosmology connects to all of this in a quiet way. If the entire cosmos can bounce, then perhaps small regions can bounce too. The same physics that might prevent a singularity at the start of time might also prevent one at the heart of every black hole. Loop quantum gravity, one of the frameworks that allows a cosmic bounce, also predicts that black hole interiors do not end in a true singularity. Instead, they might tunnel through to something else, whether that something else is a new universe, a white hole spitting matter back out into our own sky, or something stranger, remains an open question. The connections do not stop there. The cosmic microwave background, the faint glow left from our young universe, may carry hints of what came before. Some researchers have searched it for ring-like patterns that might be the imprint of black holes from a previous cycle. Others have searched for cold spots that could mark where a baby universe budded off. None of these claims has been confirmed. The patterns are subtle, the statistics are difficult, and the alternative explanations are many. What ties everything together is a single thread of suspicion. The places where our equations break down may not be endings at all. They may be doorways, the collapse of a star, the birth of a cosmos, the bounce between eons. These could be different names for one underlying process, or they could be entirely separate phenomena that only resemble each other in our limited mathematics. We do not yet know. We can only sit with the harmony of the question and notice how the smallest deaths and the largest beginnings seem, for now, to rhyme. Nothing in the cosmos stands still. The galaxies drift apart, the space between them stretches, and the rate of that stretching has been changing for billions of years, slowly, patiently, in ways we are still trying to understand. For most of cosmic history, the expansion was slowing down. Gravity tugged on everything, gently pulling matter back toward matter, and the universe seemed to be applying a soft brake to its own growth. Then, somewhere around 6 billion years ago, something shifted. The expansion stopped slowing. It began to speed up. Distant galaxies started moving away from each other faster than before, and faster still as time went on. We call the cause of this acceleration dark energy, though the name is really just a placeholder. It marks a gap in our understanding. We do not yet know what dark energy is. We only know that something is pushing the cosmos apart, and that its push appears to be growing stronger as the universe ages. For a cyclic cosmos, this acceleration is a serious problem, and possibly a serious clue. If the universe is to bounce, something must eventually halt the expansion and pull everything back together. But if dark energy keeps strengthening, the bounce may never come. The cosmos would simply stretch forever, thinning into a cold and silent fog. So the future of any cyclic story depends on the future behavior of this invisible force. One possibility, gentle in its consequences, is that dark energy is constant. The push stays the same forever, and the universe expands at a steady, accelerating rate. In that case, galaxies far from our own slowly vanish over the horizon of what we can ever see, but our local neighborhood holds together. Stars still form, atoms still bond. The cosmos grows lonely, but it does not tear. Another possibility is far stranger. Some researchers wonder if dark energy is not constant at all, but a kind of evolving field. They call one version of this idea phantom energy. In a phantom scenario, the pressure of dark energy becomes more negative over time. The expansion does not just accelerate, it runs away, it steepens, it curves up into something that mathematicians call a finite time singularity, where the rate of stretching climbs without limit. If phantom energy is real, the long, quiet future could end in a very different way. First, galaxy clusters would come unbound, their members drifting off into the widening dark. Then, individual galaxies would unravel, stars peeling away from their spirals. Solar systems would loosen next, planets sliding outward from their suns. In the last fractions of a second, atoms themselves would be pulled apart, then the nuclei inside them, and finally, the fabric of space would shred. Some call this the Big Rip, though the word feels too loud for something we do not yet know is coming. What makes this possibility important to a bouncing cosmos is that some cyclic models actually need a similar tearing event. Roger Penrose's Conformal cyclic cosmology, for instance, asks what happens when the universe becomes so spread out, so cold, so featureless that the very idea of size loses meaning. In his picture, the end of one aeon and the beginning of the next blur together because there is nothing left to set a scale, a Big Rip, or something gentler in the same family might smooth the way from one cycle to another. Other models do the opposite. They imagine dark energy weakening. In some ekpyrotic scenarios, the force that pushes our cosmos apart eventually fades, allowing a slow contraction to begin. The branes drift back toward each other. The bounce happens, cycle resets. The choice between these futures depends on the true nature of the thing we have so loosely named. The trouble is that we cannot yet tell which path we are on. Measurements of distant supernovae, of the cosmic microwave background, of the way galaxies cluster across the sky, all probe how dark energy has behaved so far. They are consistent with a constant push, but they do not rule out a slowly changing one. Some recent surveys hint softly that dark energy might be weakening with time. Others find no such drift. The numbers are close to the edge of what our instruments can resolve. So we live inside a quiet transformation we cannot fully read. The cosmos is changing its mind about its own future, century by century, billion years by billion years, and we are watching from the middle of the sentence. Whether the ending is a tear, a fade, a freeze, or a return swing into a new bang, none of these answers are written yet. The phantom force, real or imagined, sits at the heart of the question, patient and unhurried, slowly deciding for us. Look up at the night sky on a clear evening, and most of what you see appears scattered, random, like grains of salt thrown across black velvet. The stars feel placed without any plan, but the sky carries another kind of light, one your eyes cannot see, and that hidden light has a faint pattern woven through it. We call this light the cosmic microwave background, a soft afterglow left over from when the young universe first cooled enough to let light travel freely. It fills every direction, gentle and almost the same wherever you point a sensitive antenna. Almost the same. The small differences are what matter most. When astronomers map this glow with great care, they find tiny ripples of warmer and cooler light, smaller than 100,000th of a degree. These ripples are the seeds of every galaxy that ever formed. Most of the pattern fits the standard story of a hot beginning followed by rapid expansion. Yet some researchers, peering deeper into the data, claim to see things that should not be there. Faint rings, soft circles of unusual smoothness, cold spots that seem too large or too empty to explain by ordinary chance. One of the most discussed claims comes from supporters of conformal cyclic cosmology. They argue that when supermassive black holes from a previous aeon spiral into each other and merge, they release tremendous gravitational waves. If a cosmos truly recycles, those ancient ripples might leave faint circular marks on the new sky, like raindrops that fell on a pond before the pond froze over. The marks would not be bright. They would be hollow rings of slightly more uniform temperature, scattered across the microwave glow. A small group of researchers say they have spotted such rings. Other researchers, running the same statistical tests, say the rings vanish when you compare the real sky to simulated random skies. The disagreement remains unsettled. There is also the Great Cold Spot, a patch in the southern sky where the microwave light dips below the average by an unusually deep amount. It sits in a region that also seems oddly empty of galaxies. Some scientists explain it as a giant cosmic void, a stretch of space so underfilled that light passing through loses a little energy on its way to us. Others wonder if the cold spot might be a bruise, a soft echo of contact with something beyond our cycle. Perhaps a memory left behind by a different universe brushing against ours. Most cosmologists prefer the void explanation, but the void itself, if it exists, is hard to fully account for. The question stays open. Light from the early cosmos carries colors of a sort, though not the colors our eyes know. Instead of red and blue and green, it carries patterns at different angular scales, like waves on a drumhead struck long ago. Cyclic models predict that the drumhead might have been struck in slightly different ways than the standard story suggests. A bouncing cosmos, smoothly transitioning from contraction to expansion, would not need the rapid inflation that most cosmologists rely on to explain the smoothness of the sky. So the patterns might carry small fingerprints of the bounce, a gentler spectrum at the larger scales, a muted hum where inflation predicts a louder one. These differences are subtle, easily lost beneath the noise of our instruments. There is one signal that could, in principle, settle a great deal. Primordial gravitational waves, ripples in space itself, born in the first moments, would leave a swirling twist in the polarization of the microwave light. Inflation predicts a certain strength to these swirls. Most cyclic and bouncing models predict almost none. Telescopes on high mountains and frozen plains keep searching for that twist. So far, no clear detection has been made. The absence does not prove a bounce happened. It only means inflation, if it occurred, was gentler than some thought. Either possibility remains alive. What makes this light so haunting is that it has been traveling for nearly the entire age of the cosmos. It carries a story written before any star, any planet, any moon of frozen methane. If a previous cycle left even the softest trace upon it, that trace would be the oldest message we could ever read. We do not yet know if such a message exists. We do not know if our instruments are subtle enough to pick it out from the constant whisper of randomness. The patterns people have claimed to see may turn out to be illusions of statistics, or they may turn out to be the faint handwriting of a cosmos that came before. For now, the sky keeps its quiet, and we keep looking. Space, in the way we usually imagine it, is silent. Sound needs a medium to travel through, and the gulf between the stars is far too thin to carry a voice. Yet, the cosmos is not truly quiet. It hums, it ripples, it shakes, and when scientists turn those ripples into sound we can hear, the universe begins to sing in a slow, low register that feels older than anything words can describe. Consider the cosmic microwave background. It is light, not sound, but it carries within it the pressure waves that rolled through the young plasma of the early universe. Researchers have taken those pressure patterns and stretched them into something our ears can hold. The result is a deep, throbbing tone, almost like a bell struck in a vast cathedral and left to ring. If the universe truly bounces, then that ringing may be the closest thing we have to a fading echo of what came before. The question is whether anything of that earlier ring could survive the crossing. That question sits at the heart of every cyclic theory. A bounce is a violent thing, even when described gently. Matter, energy, and the very geometry of space pass through a point of extreme density. Some models say the crossing erases almost everything, leaving only the faintest scratches behind. Others say certain patterns are stubborn enough to slip through like a melody that survives being whispered from one room into another. No one knows which picture is closer to the truth. In-loop quantum cosmology. The bounce is softened by the tiny grain of space itself. Space, in that view, is made of small loops, and those loops cannot be squeezed past a certain limit. When matter tries to collapse all the way down, the loops push back. The crunch becomes a rebound. If that picture is right, then long, low gravitational waves from the prior cycle might pass through the bounce with their shape mostly intact. Some researchers wonder if those ancient waves could still be vibrating through space today, like a deep bass note left over from a song that ended before our song began. A competing picture comes from the ekpyrotic models. There, the bounce happens when two great sheets of higher dimensional space drift together and touch. The collision releases the heat and matter that will become a new universe. In that scenario, much of the prior cycle is wiped clean by the collision itself. Almost nothing survives in any recognizable form. The new universe begins nearly fresh, carrying only the broadest features of the geometry that birthed it. If that is correct, then there may be no melody to hear at all, only a faint hiss. Roger Penrose's Conformal, Cyclic Cosmology offers yet another voice in this quiet chorus. In his picture, the previous Aeon ends in a long, cold stretch where almost nothing remains but light. That light carries pressure waves of its own, generated by enormous black holes, spiraling into each other across unimaginable distances. Penrose has suggested that the ripples from those mergers might leave faint, circular patterns in the cosmic microwave background of our own Aeon. Some teams claim to see hints of such circles. Other teams look at the same data and see nothing unusual at all. The argument is ongoing and far from settled. If those circles are real, they would be something close to a recorded sound from before the bang. A whisper from black holes that lived and died in a universe that came before ours, captured in the patterned warmth of the sky. If they are not real, then the silence between Aeons remains complete, and the prior cycle remains forever beyond our reach. There is something tender in this uncertainty. We listen to gravitational waves, now with great instruments tuned to the trembling of space. We hear neutron stars spiring together as soft chirps rising in pitch. We hear black holes merging as quick, deep thuds. These are sounds from our own cycle, our own short stretch of cosmic time. But the dream of cyclic cosmology is that somewhere, buried in the noise, there might be a sound that does not belong to us, a note that started in a universe that ended before ours began. We do not know if such a note exists. We do not know if any instrument we ever build could pick it out from the background. The bounce, if it happened, may have been thorough enough to mute everything that came before, or it may have been gentle enough to let a single low tone slip through, still ringing softly under the hum of our own young world, waiting for ears patient enough to listen. Numbers carry their own quiet music, and the mathematics of cyclic cosmology hums with a particular kind of beauty. The idea is simple enough to hold in one breath, a universe that expands, slows, contracts, and bounces. A universe that does this not once, but again and again and again. The equations behind this picture are not as wild as they sound. In many ways, they are the same gentle differential equations that Einstein wrote down more than a century ago, rearranged and listened to from a different angle. At the heart of it sits a single line of math called the Friedmann equation. It is the equation that tells the universe how to grow. On one side, you have the rate at which space stretches. On the other side, you have whatever fills that space: matter, radiation, dark energy. Each ingredient pulls or pushes in its own way. Matter slows the stretching down. Radiation does the same, only faster. Dark energy, as far as we can tell, speeds it up. The whole story of cosmic history is written in the dance between these terms. In a cyclic picture, the math has to do something delicate. It must allow the stretching to stop, reverse, and then turn back outward again without breaking. Classical equations cannot quite manage this. When you run the contraction all the way down, the density climbs without limit, and the math throws up its hands. This is the singularity. It is not really a place. It is a place where the equations stop working. So the modern cyclic models tinker with the equations in careful ways. In loop quantum cosmology, a small correction term appears in the Friedmann equation at very high densities. This term has a quiet, almost shy presence. At ordinary densities, it does nothing at all. The universe behaves exactly as Einstein predicted. But when the density approaches a certain limit, near the so-called Planck density, the correction wakes up and pushes back. The math, in this version, bends the contraction smoothly into a new expansion. No infinity, no edge, just a turn. Other models reach the same outcome through different doors. In the ekpyrotic picture, a scalar field, a kind of invisible energy spread through space, does the work. As two branes drift toward each other, the field steepens. The math curves, and the bounce happens not at infinite density but at finite, manageable values. The numbers stay polite. The geometry stays whole. Then there is conformal cyclic cosmology, where the trick is even stranger. In this version, you rescale the math itself. At the end of an aeon, when only photons and gravitons drift through an empty cosmos, mass has effectively vanished. With no mass, there is no natural ruler. Big and small lose their meaning. The equations that describe a cold, infinite, empty future look mathematically the same as the equations that describe a hot, dense, tiny beginning. A simple change of scale stitches one to the other. What ties all these pictures together is a deep, almost musical respect for the idea that nothing in the math demands a first moment. The equations are perfectly happy running backward forever. They do not whisper of a true beginning. They only describe the changes from one state to the next. A first cycle, if there ever was one, is something we have added by hand. The numbers themselves do not require it. This is the strange beauty of the mathematics. The same simple ratios show up over and over. The ratio of radiation density to matter density tells you when one era ends and another begins. The ratio of dark energy to everything else tells you whether the stretch will continue or someday slow. The geometry of space, flat, curved inward or curved outward, sits inside a single number, and that number decides almost everything about the long future. What remains open is whether any of these elegant equations actually describe our cosmos, or whether they are only beautiful possibilities. The math allows cycles without a first cycle. It also allows a one-time bang with no cycles at all. It allows an eternal inflation that spawns endless bubble universes, of which ours is only one. The same gentle Friedmann equation, with different ingredients chosen, gives all of these futures. Which set of ingredients is real, we do not yet know. So the numbers sit in front of us, quiet and patient. They permit eternal return. They permit a single arc. They permit branching universes that never repeat. The mathematics does not choose. It only opens doors and waits, the way a calm equation always does, for some future measurement to tell it which of its many beautiful answers belongs to the world we actually live in. The shape of space itself may decide whether our cosmos bounces, drifts, or simply fades. This is one of the quieter mysteries in cosmology, and one of the most delicate. The geometry of the universe is set by a single subtle balance, a ratio of how much stuff fills space against how fast space is stretching. Tip that ratio one way, and the cosmos curves in on itself like the surface of a giant ball. Tip it the other way, and space curves outward, opening forever like a saddle that never ends. Between those two fates lies a knife-thin middle path. A universe that sits exactly on the line is called flat. Flat does not mean two-dimensional. It means that space, on the largest scales, follows the geometry you learned as a child. Parallel lines stay parallel. Triangles add up to the angles you expect. Light travels in straight paths that never quite meet and never quite drift apart. When astronomers measure our universe, they find it astonishingly close to flat. So close that no instrument yet built can detect a curve. This is strange. A perfectly flat universe is like a pencil balanced on its point. Any tiny nudge in the early moments should have toppled it. A little too much matter, and space would have curled up and collapsed long ago. A little too little, and galaxies would have flown apart before they ever formed. How close is the balance? In the first instance after the bang, the ratio had to be tuned to roughly 1 part in many trillions. That is the kind of precision that makes physicists pause. Some treat it as a clue, others treat it as a problem. Either way, it sits at the heart of the cyclic question, because the shape of space tells us whether a bounce is even possible. In the old oscillating models, a closed universe was required. Only a cosmos that curved back on itself could stop expanding, slow, reverse, and crunch into a new beginning. If space is truly flat or open, that classical bounce cannot happen on its own. Gravity alone will not pull a flat universe back. It will drift outward forever, growing colder and thinner with each passing age. This is why newer cyclic models had to invent other mechanisms. The ekpyrotic picture does not rely on curvature at all. It uses hidden dimensions and the meeting of two vast sheets of reality to trigger a fresh expansion. Conformal cyclic cosmology imagines the universe stretching so far and so thin that scale itself loses meaning, and the empty end becomes the dense beginning of a new aeon. Loop quantum cosmology proposes a quantum repulsion that kicks in at unthinkable densities, no matter what shape space holds. Each of these models steps around the flatness problem in its own way. None of them has been confirmed, and the question of why our universe sits on this fragile edge remains open. One idea is that inflation, a brief burst of extreme stretching in the first fraction of a second, smoothed any curvature out of existence. Another is that we live in just one bubble among countless others, and only the flat ones grow large enough to host stars and observers. A third is that some deeper principle, not yet discovered, holds the balance in place across every cycle. There is something tender about this thought. The geometry that lets galaxies form, that lets light travel across billions of years, that lets a person look up at a clear night sky, is the same geometry that may decide whether the cosmos ever returns. The thin atmosphere above your head, the gentle pull that keeps your feet on the ground, the warmth of a nearby star, all of it rests on settings that could have been otherwise. Each layer of stability is borrowed from the layer beneath it, and the deepest layer, the shape of space itself, is balanced on something we still do not understand. If the universe is truly flat, a natural bounce seems unlikely without new physics. If it is very slightly closed, the old dream of an oscillating cosmos could still be alive, hiding inside a curve too gentle for our instruments to catch. the measurements continue. Each new sky survey trims the uncertainty a little finer, and each refinement leaves the question almost, but not quite, settled. So tonight, the cosmos is balanced. Space is nearly flat. Matter is nearly enough. Expansion is nearly steady, nearly, in every direction. And within those tiny margins lives the difference between a universe that ends once and a universe that breathes forever. We do not yet know which one we live inside. We only know that the balance is real and that it is quieter and stranger than it has any right to be. If our universe truly bounces, if it cycles, if it carries echoes from before, then a strange and beautiful problem rises up to meet us. What exactly would survive the passage? What pieces of one cycle could possibly slip through into the next? And how would they be carried? This is one of the deepest open questions in all of cosmology. And tonight it sits before us, soft and unresolved, like a question whispered in a quiet room. Think for a moment about a black hole. For most of the last century, physicists believed that black holes were nearly featureless. They had only mass, spin, and charge. Everything else that fell in seemed to vanish without a trace. This idea was given a gentle, almost playful name. Black holes, they said, have no hair. Anything that made them unique on the outside was lost forever. Then, more recently, a quieter idea began to grow. Some researchers proposed that black holes might in fact carry the softest of memories, tiny, low-energy particles, gentle ripples in the fabric around the horizon, could store information about what once fell in. This delicate possibility came to be called soft hair. The mathematics is subtle, the picture incomplete, and the debate remains very much alive. Some physicists see soft hair as a genuine doorway out of the information problem. Others see it as an elegant idea that still has not shown it can carry the full weight of what is lost. The connection to a bouncing cosmos is not obvious at first, but it is there. If our universe collapsed, the matter inside it would gather into black holes long before any final crunch. Those black holes would merge, swell, and dominate the late chapters of the contraction. Whatever histories they hold, whatever soft hair they carry, would be part of the bridge into the next cycle. And so the question of what black holes remember becomes, quietly, the question of what a universe can remember about itself. Some theorists hope that information is never truly lost, only scrambled and stretched, waiting in some form on the other side of a bounce. Others suspect that each cycle wipes the slate nearly clean, leaving only the faintest statistical traces. Both views are honest attempts to face the same gap in our knowledge. Neither has been confirmed. There is another puzzle nested inside this one. If a bounce really happens, the moment of greatest density may not be a singular point, but a region where space and time themselves behave in ways we cannot yet describe. Our best equations break down there. General relativity, the language of gravity, falls silent. Quantum mechanics, the language of the very small, also struggles because the whole universe at that moment is both very small and very heavy at once. We do not yet have a theory that can speak both languages fluently. Loop quantum cosmology offers one attempt, replacing the singularity with a smooth bridge. String-based ideas offer another. With Branes meeting and parting, each gives a different answer to what crosses through, and so the lost histories remain lost. At least for now, we do not know if information is preserved, transformed, or quietly erased. We do not know if a careful observer in the next cycle could, in principle, reconstruct anything about the one before. We do not know if the laws of physics themselves stay constant from cycle to cycle, or if they drift gently, like a song played slightly differently each time. There is something almost tender about this gap in our understanding. The universe may be keeping a diary in a language we have not learned to read, or it may be a stage that is swept clean between every act, and the players who came before us truly are gone. Both possibilities are allowed by what we currently know. Both deserve to be sat with for a while. The work continues in quiet rooms around the world. Researchers compare predictions, scan the background glow of the sky, refine the mathematics of horizons and bounces, and trade careful arguments at the edges of what can be tested. No one expects a sudden answer. The questions are too old and too deep for that. But each year, the shape of the unknown grows a little clearer, even as the unknown itself stays vast. For tonight, it is enough to picture it, a long chain of universes, each one ending in a slow gathering of black holes, each one perhaps passing along a whisper of soft hair, a faint signature, a memory too quiet to read. Whether that whisper truly crosses the threshold or fades entirely in the crossing, no one yet can say. The mystery rests gently where it has always rested, waiting, patient in the dark. If our universe really does breathe, if it really does bounce, then the moment between beats may be the longest, quietest stretch of all. Picture the far future from where we sit tonight. The sun, that warm familiar star, will swell into a red giant in about 5 billion years. Its outer layers will drift away as a soft glowing shell, leaving behind a small white ember. The Earth, by then, may already be gone, or scorched, or wandering as a quiet cinder. That is only the beginning of the long, slow shift. Galaxies will keep moving apart, carried by the steady stretching of space itself. In 100 billion years, most other galaxies will have drifted so far that their light can no longer reach us. The night sky, if anyone were still here to look, would hold only the stars of our own merged Milky Way and Andromeda, two great spirals folded together into a single soft cloud of light. Then, the stars themselves begin to fade. The bright blue ones burn out first, fast and fierce. The yellow stars follow. The small red dwarfs which sip their fuel slowly may glow for trillions of years before they too go cool and dim. After that, the universe enters what some call the degenerate era, a time of white dwarfs, neutron stars, and black holes drifting through enormous dark gulfs of space. This is where the cyclic story becomes interesting again. In Penrose's conformal cyclic idea, this long cold stretch is not the end, it is the slow preparation for a new beginning. As the last stars die, and the last black holes very slowly evaporate, the universe loses its sense of scale. With no particles to measure distance, no clocks to mark time, the vast cold cosmos begins to look, mathematically, like the hot dense cosmos at the start of a Big Bang. One eon flows quietly into the next. Other theories see the long night differently. In the ekpyrotic picture, the bounce comes not from emptiness, but from a gentle collision, two branes drifting toward one another, across a hidden dimension. The universe between bounces would not need to grow infinitely cold. It would simply wait, stretched and smooth, until the next soft touch. The timing is uncertain. The wait might be 1 trillion years, or far longer. In loop quantum cosmology, the long night may be much shorter. The universe expands, slows, perhaps reverses, and then the quantum nature of space itself prevents a true crunch. A new expansion blooms outward, like a held breath finally released. In this picture, our own deep future could include a turnaround, a contraction, a bounce, all within a finite span. Each model paints a different sky for the patient watcher who is not there. The honest answer is that we do not know which, if any, of these long futures is real. Current measurements suggest the expansion is speeding up, not slowing. If that acceleration holds, a contraction may never come, and the cyclic picture would need some other mechanism, perhaps a slow fading of dark energy, perhaps a hidden brain, perhaps something not yet imagined. The data are too thin to choose. What we can say is that the universe will not stay as it is. Continents on the remaining rocky worlds will drift and collide. Mountains will rise and erode. New stars will keep forming from the gas left behind by old ones, though more slowly with each passing eon. Tiny brown dwarfs will collide and briefly flare into real stars. Black holes will merge in silent gravitational waves, ringing the fabric of space at frequencies no ear could hear. There is a strange comfort in this picture. Even in the deepest long night, things are still happening. A proton, if it decays at all, may take more than 10 to the 34th years to come apart. A supermassive black hole may take 10 to the 100th years to evaporate. These numbers are so large, they begin to feel like poetry rather than measurement. They describe patience on a scale the human mind cannot really hold. Somewhere inside that patience, the cyclic models suggest a new beginning is being prepared. Or perhaps not. Perhaps the long night simply continues, growing colder and emptier, without end. The mystery sits exactly there, in the gap between a universe that bounces and a universe that simply runs down. Both are possible. Both are consistent with what we can measure today. For tonight, you do not have to choose between them. You can let the slow future unfold in your mind. The dimming stars, the drifting galaxies, the quiet Aeons, the possible bounce still waiting somewhere far ahead. The cosmos is in no hurry, neither. In this moment are you. Step back with me now, all the way back, until our whole conversation tonight shrinks to a single point of light. From far enough away, the question of cycles becomes a question about us. We are small creatures with short lives, asking whether the universe itself lives and dies and lives again. It is, in some ways, a strange question for a being made of atoms to ask. And yet the atoms themselves are part of the answer. The calcium in your bones was forged inside a dying star. The iron in your blood was scattered across space by a supernova long before the Earth gathered itself out of dust. The carbon in your hands was cooked slowly in the cores of stars that swelled and shed their outer layers into the dark. You are, quite literally, an arrangement of star matter that has learned to wonder about stars. Each cell in your body carries a history older than the planet under your feet. Now think about what this means for the question of cycles. If our universe is a single bang, then this stardust has one long story written once. If our universe is a bounce, then perhaps the very atoms in your hand are echoes, rearranged from some earlier order that lived and ended before our sky was lit. We cannot tell the difference by looking at the atoms alone. They carry no obvious memory of where they have been. This is the deep humility of the question. We are inside the thing we are trying to understand. We cannot step outside the universe to see whether it breathes. We can only listen carefully to the light it gives us and look for patterns in the faint glow of its earliest moments. Every measurement we make is taken from within the system. Every clue is filtered through the same physics we are trying to test. And yet, look how far we have come. A few centuries ago, no one knew the stars were suns. A century ago, no one knew there were other galaxies. Within a single lifetime, we learned that space itself is stretching, that the cosmos had a hot, dense beginning, and that we can map the faint, warm glow left behind. Each of these discoveries seemed impossible before it happened. The question of what came before the bang would have sounded meaningless to a scientist 100 years ago. Now, it is a serious field of study, with equations and predictions and quiet arguments at conferences. That does not mean we will answer it. Some questions may sit beyond what any instrument can ever reach. The information we would need might be erased by the very transition we are asking about. A bounce, if it happened, may have wiped the slate so cleanly that no signal survives, or it may have left soft traces in the sky that we have not yet learned to read. We do not know which of these is true. The honest answer is that we may never know, but there is something gentle in that uncertainty. The question itself is a gift. It connects you, lying here in the quiet, to every thinker who ever looked up at the dark and wondered if the night had a beginning. The ancient stargazers who imagined wheels of time, the monks who copied star charts by candlelight, the physicists scribbling equations in the margins of notebooks. The same question, passed hand to hand across thousands of years, still unsolved, still open, still beautiful. And the same atoms too, passed from cloud to star, to planet to creature, arranged briefly into a body that can ask, whatever the universe is doing, beating slowly through endless cycles, or expanding once into a long cold silence, or something stranger than either picture, you are part of it, not separate from it, not watching it from outside. The cosmos is wondering about itself through you, for these few quiet moments before sleep. The mystery does not need to be solved tonight. It does not need to be solved in your lifetime, or in the lifetime of anyone you will ever meet. It is enough that the question exists, and that you have spent a little while in its company. Enough that the same calcium that holds you upright once burned at the heart of a star. Enough that the same hydrogen that fills the spaces between galaxies also fills the water in your body. Enough that whatever the universe is, you belong to it, completely and without exception. The bounce, if it is real, includes you. The single bang, if that is the truth, includes you too. Either way, the cosmos has made a place for the question, and the question for now has made a place for you. We have come a long way together tonight, through ideas older than the oldest stars we can see. We have stood beside the thought of a cosmos that breathes. We have looked at brains drifting toward one another in higher space. We have wondered if a black hole might be the seed of a world we will never visit, and through all of it, the central question has stayed soft and open, the way questions are supposed to stay, when no one yet knows the answer. Was our Big Bang the first thing that ever happened, or only the latest beat in a rhythm that has no beginning and no end? We do not know. We may never know, and there is something quietly beautiful in that. Picture, for a moment, a small blue world turning in the dark. Its oceans rest under a pale moon. Clouds drift slowly across the night side, lit faintly from within by distant lightning. Somewhere on that world, a single window glows. Inside the window, someone is falling asleep, listening to a voice talk about the shape of everything. That someone is you. And the universe, whatever it truly is gentle enough to hold you while you rest. Far above that quiet world, the galaxy turns. It turns so slowly that no human eye could ever see it move. A full rotation takes hundreds of millions of years. Stars are born in its arms, and stars die there. And the dust of those deaths drifts together again into new suns. Nothing is wasted, nothing is final. Even on the smallest scale we know, the cosmos seems to prefer cycles to endings. Maybe that is why the idea of a bouncing universe feels so close to the bone. We are made of atoms that were once inside other stars. The carbon in our hands once burned. The iron in our blood was forged in a furnace older than the earth. We are, in a real and gentle sense, a cosmos remembering itself in a new form. Whether or not the whole universe bounces, the matter we are made of has already lived many lives. Some researchers will keep looking for the soft echoes in the background glow. Others will keep working on the mathematics of branes and loops and conformal aeons. Still others will argue that there is only one beginning, only one arc, and that the search for prior cycles is a search for ghosts. All of these people are doing the same thing, really. They are pressing their ears to the wall of the universe, listening for something on the other side. For tonight, none of that needs to be solved. The equations can rest. The telescopes can keep their long, patient watch without us. The question of what came before the bang and what may come after the long, cold night can sit beside your bed like a candle that does not need to be blown out. If the cosmos truly does bounce, then somewhere far ahead in time, long after every star has faded, the conditions for a new beginning will quietly arrange themselves. A new burst of light, a new set of laws perhaps, or the same ones written again in the same patient hand. New worlds, new oceans, new windows glowing in new nights. And if it does not bounce, if this is the only arc there will ever be, and what we have is still extraordinary. A single, unrepeatable cosmos, a single chance for galaxies to form, for planets to cool, for someone on a small blue world to listen to a quiet voice and drift towards sleep. Either way, you are held by gravity, by atmosphere, by the slow turning of a world that has carried life for billions of years, held by a universe that, whatever its shape, made room for you in it. That is not a small thing. That may be the largest thing of all. So let the question stay open. Let the branes drift in their higher space. Let the aeons follow each other in Penrose's strange and lovely picture. Let the loops uncoil and recoil in the deepest mathematics. None of it needs your worry tonight. The cosmos has been doing what it does for a very long time, and it will keep doing it long after this small moment of listening has ended. Breathe slowly. Let your shoulders soften. Let the dark behind your eyes become the dark between the stars. The universe is vast and quiet and far older than any answer we have found. And it is, in its own slow way, kind. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.